Hey everybody, welcome back. And today we're going to be finishing our look at related rates with an interesting problem, I think, involving zombies, of course. And I think this is our very last zombie problem for the chapter. So enjoy it while you can. Let's get going. Here we have one of my favorite zombie movies. We got Shaun of the Dead. It is a kind of a comedic zombie movies, but it's got some pretty solid zombie tropes in it, I think. So one of my favorite zombie movies. Definitely check it out if you haven't seen it. So here we go with a problem which is not particularly about Shaun of the Dead, but is a zombie thing. So to protect your fellow survivors from zombies, your group digs a trench with cross sections in the shape of a triangle with the vertex oriented on the bottom. The trench is going to be 3 meters deep, 5 meters across, and 20 meters long. If the trench is filled with water at a rate of 48 liters per minute, how fast is the water level rising when the water in the trench reaches 2 meters deep? So there's a lot to this question, really. And for our understand the problem, we're again going to use the same 6-part plan. We're going to try to understand what that looks like. And rather than trying to draw everything here, I'm just going to refer to our diagram here. We're going to pretend that we are actually looking at a triangle here. So well, that's not that great looking of a triangle. And hold on. One of the things you're going to have to buy into for this problem is that this trench is in the shape of a triangle, like we see here, inverted so that the bottom of the triangle, the vertex of the triangle, is at the bottom. And then they did give us some dimensions here. So this across, I believe that was 5 meters. And this was 3 meters, I think. I'm probably wrong. Let's go check. How far across? 3 meters deep, 5 meters across. So I got that exactly backwards. This is 5 meters across this way. This is 3 meters straight up and down. So that tells us a lot about the triangle already. And let's see where we go with this. Okay, so the trench and the water inside the trench, incidentally, is in the shape of a triangular prism. So triangular prism, remember the one side, the front side is a triangle. The back side over here is also a triangle. And then they are connected with the rectangular planes. So that's our trench. Now, the volume for any trench is the area of the base multiplied by the height of the trench, or the distance between the two triangular bases. The area of the triangular base is 1/2 base times height, and we're going to say L is the distance between those two bases. Basically, this is L from the front to the back. Lowercase b, lowercase h. So is there anything here that's constant, either lowercase b, lowercase h, or L? Well, in terms of the water in the trench, L is always going to be 15. The water is always going to go all the way across that at 15 meters, I believe. So the length of the trench is always constant, which are variable. Okay, so which of these are variable? Well, B is variable, and H is variable. Both B and H are variable. Okay, that means that we can substitute L immediately, but we can't substitute either B or H. Okay, so as water enters the trench, it fills from the bottom up as shaded. So taking a look at this diagram over here, this is the water in blue, and obviously it's blue because it's water. And as this fills up, hopefully you see that there are two triangles here. Okay, we've got one triangle here, the larger one, And then the other triangle is going to be this triangle in green, the entire shape. Those two triangles are important to us because they are similar triangles. Okay. The blue triangle has a base of b and a height of h. These are both changing, and that means that the dimensions of the water are changing. And then the other triangle has a base of 5 and a height of 3. Now that's constant. That's not changing. So we've marked them on our diagram. And then this is the key step. I like how that's under no uncertain terms here. We know this is the key step. Okay, because this is going to allow us to simplify our model. If we take these two triangles apart, they look like this. What do we know about these two triangles? Well, I can tell you, if you take a look at these two triangles, this angle at the bottom, the vertex, is literally the same as this angle here, the vertex of the water. And then also, this angle here is exactly the same as this angle here, and is also the same as this angle over here. We know that because we have parallel lines. This line over here is parallel to this line over here, and that gives us that corresponding angles of parallel lines are congruent. Bet you didn't think you'd see the geometry here, did you? So these two triangles are similar by AAA similarity. You only needed two angles, but we might as well go with all three. These are two similar triangles, so the dimensions of two similar triangles are in ratio. So in other words, because b is equal to 5 on the big triangle and h is equal to 3 on the big triangle, that means b on the small triangle should be equal to 5/3 h. Always. The base length of the water triangle is always going to be 5/3 the height of the water triangle. We can use this similarity then to simplify our primary equation, basically. Okay, so 3, we're going to write our equation, and we're going to substitute all the constants, and then we're going to substitute b equals 5/3 h. That gives us 1/2 of 5/3 h for the b. Let me just equate those for you. B was 5/3 h. And then also L is 20. So half of 5/3 h L is half of 5/3, half of BHL is half of 5/3 h 20, which is just 50/3 h squared. H is variable, it's changing. V is also variable, it's changing. So we cannot substitute any further into this equation. See how those substitutions made this a lot easier? So it's a lot easier for us to take our derivative now. So let's take the derivative. The derivative of v with respect to time is equal to the derivative of 50/3 h squared with respect to time. 50/3 is constant. So the only thing I need to take a derivative of is h squared. So what's the derivative of anything squared? Well, we went over that last time. The derivative of anything squared is 2 times that anything multiplied by the derivative of the anything. So 2 times h dh dt, and that simplifies for our dv dt into 100/3 h dh dt. It's not worth simplifying 100 over 3. Just leave it the way it is, and at the very end, we'll just multiply it all out. Good thing for you to do. Next, we're going to substitute any of the quantities that are depending on time. So this goes along with what I said last time. After we take the derivative, then immediately we're going to substitute. So dv dt, well, we know how fast the volume of water is increasing because we know how fast our hose is going. We had that at 0.048. 100 is constant again. Currently, h is at 2 meters, and dh dt is unknown. Now look at this equation because it's so easy now just to solve for dh dt. dh dt is at 0.048 multiplied by 3 divided by 200. And that gives us a dh dt of 0.00072 meters per minute. So basically that water in that 20-meter long trench is, the water level is going up very, very slowly. Let's interpret that solution. When the water in the trench is 2 meters deep, the water level is rising. And that's a more contextual way of saying increasing, really. Height is increasing, water level is rising. Means the same thing in this context. At a rate of, there's that number, 0.00072. And our units, meters per minute. So that took a really difficult problem, and it made it pretty easy, I think. Maybe it's because I've been doing this for a long time, but this doesn't seem too bad. I shouldn't say that. That's going to, well, let's just forget that any of that happened. Anyways, dh dt, let's remember that dh dt is the rate that this h is increasing, and h is the height of the water. So that's the rate that the height of the water is increasing. So for these problems involving solids being filled or empty, the similarity of dimensions will often be used as a secondary equation. Now remember that a secondary equation is the name that we give to any equation that we use to reduce the complexity of our primary equation. And since this is contextual, be careful of the units. Make sure that the units always match up. Every year there's always my answer isn't correct. It doesn't look like what it says in the book. But actually it is the correct answer. It's just that the units didn't match up correctly yet. So let's get to this check your understanding. We've got ourselves an inverted plastic cone that's 20 centimeters in diameter and 20 centimeters in height. And it's being filled with sand at a variable rate so that when the height of the sand is always increasing at a constant rate of 2 centimeters per minute. Well, that's kind of an interesting thing to do. Think about how would you engineer it so that the height is always increasing at 2 centimeters per minute. So, at what rate is the volume of the sand increasing when the sand is 10 meters high? So, let's unpack this a little bit. We see the rate that the volume of the sand is increasing. That's a dv dt. We have the height of the sand increasing. That's a dh dt. And notice that here we have a cone inside of a cone again. 2 cones. So the inner cone and the outer cone share the same base angle right over here. And they also share, let me get a more suitable pen. They also share the same angle over here, just like with the previous example. So these are similar cones. Yet again, similarity. And we can do almost the exact same thing we did for the previous problem. The similarity really helps you out here. So let's understand the problem. I think we got that. As the cone fills with sand, the solid of sand, and solid basically means the shape is a solid, not that the sand is, somehow glued together or anything like that. The solid of sand will create a similar cone to cone with the outer plastic cone. That's a lot of cones in one sentence. So let's build our mathematical problem. We should probably start off with the volume of a cone. That's 1/3 pi r squared h. And then because of similarity, well, let's take a look over here. The base is 200. The base of the cone is 200. And the height of the outer cone is 20. I'm sorry, not 200, 20 and 20. So over here, this base and this height should be in that 20 to 20 ratio as well. Now the formula here is radius. So if this is 20, that means the radius is 10. So really, the radius is half of the height, which is what we have here. The radius to height ratio is 10 to 20, or the radius is half the height. Now for number 3, we're going to write the equation relating the variables. Basically, we're going to take the volume equation and we're going to substitute into it. So if we have our 1/3 pi r squared h, then we're going to substitute this r with 1/2 h. So when you square that, you get 1/4 h squared. You multiply it by the h, and now it's 1/4 h cubed. And then you multiply by 1/3, now you get 1/12 h cubed. So volume is 1/12 pi h cubed. Let's take the derivative of both sides. The derivative of volume is equal to the derivative with respect to time of 1/12 pi h cubed. What's the derivative of something cubed? Well, the derivative of anything cubed is 3 times the anything multiplied by the derivative of the anything. So 3h squared dh dt. Multiply that by the constant pi over 12. And you get yourself that dv dt is 1/4 pi h squared dh dt. Penultimate step here is to substitute all of the variable quantities now, including the derivatives. H was currently 10, and dh dt was +2, positive because h is always increasing. And when it simplifies, you get yourself 50 pi, which is 157.07963. Lastly for chapter 5, we're going to interpret the solution. And when the height of the sand in the cone is 10 centimeters, the volume is increasing at a rate of 157.079 cubic centimeters per minute. So keeping the same format here for everything that we are writing, all of our interpretations, that should decrease the cognitive load on you for these problems. So that's it for us on chapter 5. Good luck with the rest of the related rates. Good luck with the chapter, and see you next time when we start chapter 6. Have a good one.